All right, 10:40. You guys sufficiently caffeinated? Ready to hear about generators now? Yes, exactly. That's exactly what I wanted to be doing in my morning. The talk is hanging up on callbacks. The story behind this, I came up with this topic at work, and I was like, I wheeled around in my chair, and I turned to my coworkers like, I got it, hanging up on callbacks. Like, you're done with callbacks. You're hanging up on them. And it was like straight faces around the room. Yeah, all right, well, I got some laughter here. Have any of you seen this talk before, or can I tell all the same jokes that I tell whenever I give this thing? Yeah, all right. Okay, so hanging up on callbacks more than flow control with ECMAScript 6 generators. If you can't be bothered to sit here and watch me read slides to you, and you want to like play around with some examples on your own, you can hit this URL. I've got some working examples of generators doing a variety of things that you may want to do in a regular web application. You're going to need, I think Firefox 27 will run these. Chrome Canary will also run these examples. But if you try to hit this URL and your web browser pukes, then you need to go upgrade your web browser because this stuff is cutting edge. Okay, so about me, the obligatory about me slide. I'm a developer at Carbon 5. We've got an office in Santa Monica, down in LA, and we've got an office here in San Francisco. I am down in the Santa Monica office. Makes me kind of sad. I like the weather, but I'm from Seattle, so I got to hate on that city. Oh, my thing died. Everything died. So do a little Haskell, use Vim, some Ruby, some Python, some JavaScript, and stuff like that. This means that like I'm hip in LA, but I come back here to San Francisco, and everybody's using Vim and writing Haskell, so I don't really have much to rep. So this presentation is about turning code that looks like this, which many of you write in your day jobs. Got some synchronous operations and some asynchronous operations. I'm doing a bunch of stuff to try to like centralize error handling across different ticks of the event loop. It's a sloppy mess of stuff, but we got to do it anyways until generators show up. This is the same code functionally as this. You're able to write direct style programs, centralizing centralizing error handling across event loop ticks, using some new functionality that you're going to see later on that's part of the ECMAScript 6 draft specification. Out of curiosity, any of you Node people already? Any of you use Node fibers? Yeah? Okay, all right. You guys have heard everything that I'm going to say, so you can leave, and the rest of us, we'll keep talking about generators. Node fibers are very similar to ECMAScript 6 generators. The yield semantics are a bit different, but you're going to see some stuff that's going to look familiar. Specifically what this is about, it is my position that programming around asynchronous callbacks is hard, especially for people that are used to synchronous direct style programming that you're going to see in Python, Ruby, and Java, and so on and so forth. ECMAScript 6 generators, the draft specification, talks about generators, which I'll demonstrate helps you relieve some of this pain, and actually conceptually allows you to do something interesting that continuations do not. Continuations, for those of you that don't know what I'm talking about, is a common paradigm in JavaScript programming where you ask the computer to do something, and then along with what you're asking the computer to do, you tell it what to do next. That's your callback. Direct style programming, you're going to ask the computer to do something, and you're going to get something back. We can write direct style programs using generators without losing the power, the concurrency power of the single-threaded JavaScript event loop. Kind of interesting stuff. Okay, so I'm going to enumerate some problems, my gripes about programming around callbacks in JavaScript land. It's my position that, especially for the uninitiated, it is a non-trivial amount of effort to follow the path of execution through a JavaScript program that is laden with asynchronicity, especially when you're mixing synchronous operations with asynchronous operations. This is like the super noob example that many of us fell for when we first started writing JavaScript, either on the server or in the browser. You can just imagine that _get is an alias to your favorite HTTP request making asynchronous library. And so on tick 1 of the event loop, I'm declaring a variable message. I'm setting it to some string. I'm doing some asynchronous operation. And I'm saying when the result of that asynchronous operation completes, I want you to concatenate the name from the profile onto message, and then I want to output it to the console. But as we all know, because we're super elite JavaScript programmers, this doesn't work. You're just going to get hello, because console.log is a synchronous operation that is going to fire before the callback for this asynchronous operation concatenates the profile name onto that message variable that's accessible via the closure. So new JavaScript programmers do this stuff all the time. I pair program with our client developers that may have more experience in Ruby and Python, and they bonk their head against this. And it takes a little bit of time for them to sort of understand how the JavaScript engine is working such that they don't fall for this kind of stuff. Other thing, gripe, is that handling exceptions across event loop ticks, or handling errors across event loop ticks is a pain in the butt. Try and catch only work for synchronous operations, or rather like operations that occur on the same tick of the event loop as you are evaluating the try-catch. So this is the example I showed in the beginning. We'll sort of step through what's going on. So you can imagine that getData, some lib.getData is a synchronous operation. And when it raises an error, we can catch it with try-catch. That's awesome. Then I want to plumb this back to my, my centralized exception handling stuff. I'm going to write to some log file. I'm going to read through the error and maybe bring down the process or something like that. That's all well and good for synchronous operations, but what about these asynchronous operations? HTTP request to /foo or an HTTP post to /bar. If their callbacks follow, let's just assume for a second that their callbacks follow the node style syntax of like error first and then some number of values afterwards. Because the error is going to be available on a future tick of the event loop, a different tick of the event loop than when our try-catch was evaluated, I have to plumb this error handler around via closure. It's a ton of code to write. It's a bunch of boilerplate grossness, and I don't like doing it. There's got to be a better way. There is a better way. I'll show you. OK, third gripe, AsyncFlow Control is kind of a pain in programming in the world of asynchronous callbacks, especially if you want to mix things that run concurrently with things that run in series. So this is just a vanilla JavaScript example of us doing two things at the same time, and then when their results come back, then we're going to do some things in series. So you can imagine that I'm going to do my request, two asynchronous HTTP requests to get a token and get a key. When their data comes back from whatever remote system, I'm going to execute these callbacks. And in the callbacks, I'm going to check to see if I've got the data from both callbacks. So this is doing two things I'm going to say concurrently. We're doing two things concurrently. And when both the results come back, then I'm going to execute my login function. Login function is going to do a post to auth using that data. And then finally, we're going to do a window.location.redirect. So we're doing two things concurrently, and after that comes back, we're doing some things in series. It's a bunch of boilerplate code that we have to write, namely this like if login token and login key. It's sloppy. And furthermore, getting the token and what to do next are two things that are tied together. What if we want to get a token and we don't then want to like log in? We have to move some code around. We can write some higher order functions to like plumb the return value, or excuse me, the token around, et cetera, but it's a pain in the butt. Promises make it a little bit easier. We're going to do the same thing functionally. We're going to like issue an HTTP request for token and an HTTP request for key. We're going to wait for both of those promises to resolve. That is to say, we get the token and the key. And then we're going to do that post to auth, which we're just going to assume returns a promise. And then finally, we're going to do the redirect to dashboard using that result. So functionally, the same code as we had here before. There are a few less lines, but there are still a lot of lines. Async gives you a very explicit way to manage flow control in JavaScript. That is a seriously large amount of lines of code to scrutinize. And it might actually take you a while to like squint at all that async stuff and try to think like, what is going on? I've got like waterfall and parallel and what is that? You can write some higher order functions to dispense of the intermediate anonymous function expressions that you're passing to parallel. but it's still a lot of code. It is like way more code than I want to be writing. If all I really want to do is to do two things at the same time and then do some other stuff, there's got to be a better way to express that. This is super imperative. There's got to be a more declarative way to express this. Okay, so my whole value prop is to sit around and tell you about how generators are going to save you from things, from this type of problem. What generators are, I'm not going to read that to you, but essentially they are functions that are different than the types of functions that you're used to writing in JavaScript today. So the JavaScript functions used to writing, you enter in at the top and you exit at the bottom. Generator functions are different in that they could be entered in different places. These generator functions, you initialize them, you start at the top, and you can suspend them and then later re-enter at some strange part, some different part of the function body, not necessarily just at the top. You may be thinking to yourself, as I was talking about ECMAScript 6, draft specifications, like, okay, I write real computer programs for like IE8, like what am I to do? You can use this stuff in ES5 compliant browsers today as long as you're willing to introduce a compile step. Since many people are already writing CoffeeScript, introducing something like Google Traceur to transpile from ES6 to ES5 is not like the hugest of sins. But if you just want to play around with this stuff and you don't want to do this transpilation step, you can play around with it in newer versions of Firefox and Canary. I think it's going to be a while before the major vendor browsers, the major browser vendors start to pick these features up. It's still a draft specification anyways, so I think it would be a little premature for us to expect that that stuff be available now. You can use this stuff in Node 0.11 with the Harmony flag. And as I mentioned, I've got those examples up on the web. Okay, generator basics. This Fibonacci sequence generator is like the hello world of generators. If you look at Python generators, they always talk about Fibonacci sequence. It's a perfect example of how to generate, or how to use a generator to express an infinitely long list without computing the entire list all in one shot. So you'll notice some interesting syntax here. First thing is this little star after the word function. That denotes that this is a generator function. It behaves fundamentally differently, in a fundamentally different way than the functions that you are used to writing. The yield keyword, the yield operator, is also new. If you try to evaluate this code in a browser that does not implement the ES6 generator feature, you're going to blow up. It's not going to know what that star is. And it's also not going to know what the yield is. Yield operators can only exist inside of generator function bodies because yield wouldn't really mean anything if they were in a regular function. So, okay, so in explaining this example, you can imagine these two pieces of code are just on top of each other in the same file. I put them next to each other to demonstrate bouncing back and forth between the generator function and the caller of the generator function. All right, so here we go. So first thing I'm going to do is I'm going to call the generator function. And what that's going to do is it's going to initialize the generator function. It's going to give me back a generator object with some methods on it, like next, as you're seeing there. Important to note is when you call the generator function, you've only initialized it and got this object back. You actually haven't started evaluating the code in the function body. So we've initialized it. Now we've got a hook to our generator object stored in this seq variable. I don't know why I called it seq, maybe sequence of something, doesn't really matter. Next thing I'm going to do is I'm going to invoke the next method on the generator object. That is going to start evaluating the generator code, the code in the generator function body from top to bottom. So I'm going to do some variable declaration. I'm going to declare A, I'm going to declare B, I'm going to declare C, and I'm going to do some assignment. And then I'm going to hit this while, and I'm going to evaluate the expression on the right side of while, which is true, because I typed the word true in there. And then I'm going to hit my first yield operator. And what that's going to do is it's going to yield the result of evaluating the expression on the right side of the yield operator back to the caller of the generator function. So, and the other thing it's going to do is it's going to suspend the generator function. So with some substitution, since A started at 0, A is going to be made available via the value property of the return object from that call to next. And the generator function is like frozen. It's frozen right after that yield A. Then when we call next again, we're going to re-enter the generator function. We're going to resume the generator function immediately after the point in which we suspended it. So then we continue down through the rest of the code in this while block. We're going to do some assignment. We're going to get back up to the top. True is still true and will be forever. And then we hit yield again. So now A is equal to what? Pop quiz. And I refuse to go until somebody tells me the answer to this question. Thank you. All right, so then we yield, suspending the generator function, we yield the value 1 back to the caller, and the generator function is suspended. So you can sort of imagine like where we're going here. Every time we call next and dereference the value property from the return object that we get from calling the next method, we get another iteration of this while loop. The generator function, as long as we are not evaluating code inside of it, is in a suspended state. And you can resume it if you want to, as long as there's more code left to evaluate. All right, so slightly more advanced example. It seems a little trivial, the example, but it's important to understand the semantics of generators such that when we get into the more complex examples, like how you would use this stuff in building a real web application, you sort of get what yield means, you get what it means to resume and suspend, and so on and so forth. Okay, so another pop quiz. And all you people that like are already familiar with coroutines in Node are not allowed to answer. But let's assume that we evaluate these 3 lines of, well, let's assume we evaluate the whole thing. And assume that log is an alias to console.log. What do we see in the console? We're going to see 3 things. What are those things? I ask these questions so I can feel smart because I already know the answer. Anybody? One guess? All right, I'll show you. Okay, so just like with the Fibonacci sequence, the first thing we're going to do is we're going to invoke our generator function, which is going to initialize it. The return value of that initialization is going to be our generator object, which has that next method on there. So we haven't started evaluating the POW generator function body yet. We've got this G variable whose value is a reference to this object. We're going to call next on it, which is going to start evaluating the code from top to bottom in the POW generator. So first thing we're going to do, we're going to declare our variables, and then we're going to start evaluating the code on the right-hand side. Based on regular order of operations in JavaScript, the arguments to this math.pow function are going to be evaluated first. So we're going to hit our first yield operator. And we're going to evaluate the expression on the right side of yield, which is just a string literal, A. And we're going to suspend the generator function, yielding A back to the caller. So with substitution, you can imagine that the first thing that we're going to log out to the console is just A. Next thing we do is we resume the generator function, only this time, unlike in the Fibonacci sequence thing, we're going to pass something to the generator function. In this scenario, we're going to pass the number 10. What it does here is when we resume the generator function, we're going to insert that value immediately after the point in which we had suspended earlier. So we suspended after yield A, and now we're passing 10 down here at the bottom. So 10 is going to be inserted where we resume. We hit our next yield expression, which is going to suspend the generator function and give the string literal B back to the caller. So now we've output A and B to the console. The generator function is in a suspended state. Last thing we're going to do, we're going to resume the generator function with the number 2. Via substitution, you can imagine this is inserted here. And now we evaluate the rest of the generator function. We're going to take 10, we're going to raise it to the power of 2, we're going to store it in result, and then we're going to return it. So, final answer, you're going to output A, and then B, and then 100 to the console. And you can sort of see how you're bouncing back and forth between the caller of the generator function and the generator function body itself. Okay, Fibonacci sequence, awesome. Raising 2 to the power of 10, also awesome. But like, how are you going to use this in the real world? I was griping earlier about following the path of execution through a program written around asynchronous callbacks. And I was also whining about how when you're asking the computer to do something, you also have to pass a set of instructions that tell it what to do next. With generators, we can decomplex these two things. So we can, using a little boilerplate code, we can ask the computer to get us a profile, and we can write a generic sort of way to get a hook to those values that come from it. This syntax kind of looks a little familiar. We've got a little star after our generator function. but we've introduced this new function called Cinq. Cinq, whose implementation I'll talk about in a little bit, is just a helper function that facilitates the starting and the stopping and the yielding and suspending and passing values around with generator functions. There are a variety of libraries out there that do this type of stuff for you. CO, GenRun, Jenny, there are a ton of them. And as the specification gets more and more close to being a real thing, you're going to see way more of these libraries. I wrote one that we'll walk through the implementation of in a moment just to demonstrate how you could write some code to facilitate this bouncing back and forth stuff. Okay, so what's happening here? Cinq is being passed an anonymous generator function. So I don't have a name, it's just a generator function expression. And that generator function expression is being passed a function that we are passing as the callback to our asynchronous operations. We don't even know what that thing does. We just read the docs and we know that its job is to resume our generator function after we've done some asynchronous thing and suspended. The implementation of this Cinq method is pretty basic. It's not all that robust, so don't go copying that and running your multi-million-dollar business on my Cinq implementation. But you can see that in this implementation, we're doing things very similar to what we were doing in those Fibonacci sequence and power raising examples. So when we call Cinq, we're passing a generator function. We're immediately going to initialize the generator function. That's the iterable equals gen called with resume. We're going to store that iterator, and then we're immediately going to call next on it, which is going to start evaluation of that code from top to bottom. Notice from top to bottom means we're going to do this asynchronous operation, get profile, and we're going to pass this resume function that our generator function was passed. The generator function is passed that on the third from the last line where we're doing the initialization. So we're calling the generator function, we're passing this resume function. The resume function's only job is to be handed off to the runtime such that when our asynchronous operation completes, it, assuming that you've got a return value from your asynchronous operation, will resume the generator. This example assumes that all of your asynchronous callbacks have the same signature, which serves me really well in this talk, but does not actually happen in the real world. You would have to do some interesting things like you'd have to write variadic functions to make sure that if you got like 10 return values and error was first, that you passed all 10 return values back to your generator function. But just bear with me for now. Assume that you either get an error first or you get a return value. If we get a return value, we're going to resume our generator function with that return value. So what that allows us to do is, let me get back there, is we suspended the generator function. We're waiting for our profile to come back. When we get that profile, we will fault that value in for where the yield get whatever is, and we'll assign that to profile, and then we can do hello, Joe Bob, or whatever your name is. So we're combining asynchronous operations with synchronous operations without the addition of a ton of syntax. Just this yield stuff, this generator function, and then a little glue that hopefully somebody else will write for you. Okay, second gripe. I was talking about centralizing exception handling across different ticks of the event loop, right? Like we're plumbing this on-error function via a closure around everywhere, and we have to do this like if error, execute our error handler stuff. It's a pain in the butt. We can't use TryCatch because TryCatch only works with synchronous operations that raise errors in the current tick of the event loop. But we can do a whole lot better with generators. Now, in this example, we're using TryCatch to catch not only errors that are raised due to something being thrown in a synchronous operation, but we can also use this stuff to catch errors that are the result of an asynchronous operation. So yield post foo, yield post bar, those are both asynchronous operations whose callback is this resume function that the Cinq library has implemented. What that looks like is a simple modification to our resume function. In addition to resuming a generator function with a value, you can resume a generator function immediately raising an error. So you can imagine that if your asynchronous operation has, for its first argument, an error value, you can resume the generator function, and right at that point in the function body where you resume, it'll raise, which allows you to use TryCatch that is like already built into the language. You don't have to do this plumbing of your error handling stuff all over the place to handle the fact that code is executing at different points in the event loop. And that's awesome. Third thing, AsyncFlow Control. I was talking about combining notions of doing things concurrently with things being done in series, and how there are some libraries that help manage that complexity. This is once again the example of doing it yourself with raw JavaScript, but the same thing can be completed super easily using generators. A quick aside, this example has been modified to support this concurrent operations thing that I'm talking about. So once upon a time, we were passing this resume function into your generator function. Now we're passing a higher order function. Does anybody raise the fingers, know what I mean by higher order function? Like a function that returns a function? Yeah? All right. So this function's job, this res function, is to, when you call it, increment a counter, and when its function that it returned to you is executed, decrement the counter, check to see if that counter is 0, and if the counter is 0, then resume the generator function. That allows you to like stack up a bunch of asynchronous operations and not resume your generator function until they've all completed. And once again, this is something that like all of these generator libraries will do for you, code, gen run, all that stuff. The implementation of it is not particularly exciting. You'll notice that now the resume function has a little bit more smarts to it. It used to just check to see if we had an error or a result and resumed our generator function. Now it's going to return a function that is going to take whatever value we got back from the result of our asynchronous operation. It's going to jam it into this array. The offset is important. When all of the values have come back, we're going to resume the generator function. So I'll just step you through what that looks like, and then I'll get off the podium. So first thing we're going to do, we're going to evaluate. Let's just assume that we've started the evaluation of our generator function body. We're going to do our declaration of the data variable, and then we're going to hit a yield expression, or excuse me, a yield operator. As we all know from looking at those other examples, what we're going to do is we're going to evaluate the expression on the right-hand side of yield, which is this array. We're going to follow the regular order of operations in JavaScript. We're going to hit the leftmost slot in that array, and we're going to evaluate that expression. But that expression also has an expression inside it, which is this higher order function that we passed. So we're going to call res, which is going to increment that counter and tell our library, like, whoa, like we are waiting for one asynchronous operation to complete. That's going to return a function that we pass as the callback to our asynchronous operation. Great. The return value of these asynchronous operations is typically going to be undefined. The return value actually doesn't matter to us. It's the value made available in the asynchronous callback that's the real important stuff. Asking the remote server for some data or whatever, the return value of asking the server for that data is actually not important. It's when the asynchronous callback fires that's the important stuff. So then we're going to do this second slot in this array, which is the same old thing. It's going to be an asynchronous operation to post. Following the order of operations in the language, we're going to call our function that we were passed, which is going to return a function, which we're then going to pass as the callback to post. And then we suspend the generator function. So now Cinq is just hanging out, waiting for these asynchronous operations to complete. When both of them are completed, it's going to decrement a counter to 1 and then decrement a counter to 2. And then it's going to, when it gets everything back, it's going to resume our generator function. So then we have some values made available in an array. The point that I'm trying to make here is that you can do things you can do things concurrently and things in series simply by using the yield keyword, some library to handle all this boilerplate stuff for you, and an array. We can continue evaluating through the rest of this code. We've done those two things at the same time. Now we're going to go down to the next line and do another asynchronous operation. This looks pretty similar to the other examples we've seen, where we evaluate that higher order function, pass the resulting value into our post function, suspend the generator function until we get our answer back from the server or whatever, fault in the value, and then just continue plowing from top to bottom. So it's an easy way, with a very few amount of characters of code that you actually have to type into the computer, to combine things being done concurrently with things being done in series. Okay, so yammer, yammer, yammer. I talked about all these examples and stuff. My point is that generators enable you to write direct style programs, even though you are doing a bunch of asynchronous stuff under the hood. This does not block your single-threaded event loop. It just suspends generator functions pending the resolution of your asynchronous operations. You can already try this stuff out in Canary. You can try this stuff out in Node, and you can try this stuff out in Firefox now. And if you're fine with the transpilation step, you can transpile from ES6 to ES5 and use them in some legacy browsers. It's my position that as these things become not a draft, but a reality and implemented by the vendor browsers, that they will dramatically reshape the asynchronous code that you're seeing online today. So go experiment, check it out. Highly recommend you check out task.js, which I think is written by the Mozilla people. That is an interesting combination of promises and generators. Toby Ho, Tim Caswell, and Andy Wingo on the V8 team have all written about generators and been writing about generators for a number of years. So I encourage you to check out their work. And this is all my stuff. So come read about generators or other things. Thanks. You guys got any good stump the speaker type questions? Huh? All right.
Any performance concerns at all?
Negligible compared to, I mean, this is like my canned answer, but like negligible compared to the amount of time you're going to spend waiting on I/O. From a memory perspective, not really. Andy Wingo wrote about generator performance in V8, and the difference between using straight up callbacks versus generators was like tiny, tiny fractions of the total amount of time it took to like do much of anything. And that's been my experience playing around with this stuff as well. I don't really notice it at all. And given the fact that like you can now compose asynchronous operations, it's like totally worth the marginal penalty.
So the utility function Cinq,
Mm-hmm.
why wasn't it made part of the standard?
I don't know. That's an interesting question. My guess is because as far as I interpret, the ECMAScript 6 specification doesn't really know much about asynchronicity per se. Like this is an implementation thing, right? Like JavaScript, the implementation like happens to be this asynchronous programming language, but ECMAScript itself, I don't really know that it was certainly like practically speaking, like we all write asynchronous JavaScript, but I don't think it would have fit into the specification. But that being said, there have been people that have been plowing through these implementations, building like Genrun and CO and Jenny and stuff like that for some time. Some of whom actually work very closely with these committees that are actually like building out the ES6 specification. So I have a pretty high degree of confidence that it's going to be the artifacts that they are producing are going to be robust and useful. But I don't know why it didn't make it into the specification itself. It's an interesting question. Yeah, what's up?
Can we go back to your last example with the two guesses you're doing at the start?
Mm-hmm.
Or sorry, to get the post. Is there something that's preventing having each of those on the first line return a promise, and then using promises all instead of having to call res as a function, making a function, higher order function?
Yeah, totally. And in fact, the task.js library does something like that. I think that promises are interesting because they provide like a uniformed API around which you could build some of this like stuff like we built with Cinq. If get return to promise and you yielded that, then Cinq would be in a better position to like reduce even more of this boilerplate code for you. I didn't write that into the examples because then you'd have to like understand promises in addition to understanding like the asynchronous stuff. But you're totally right. Like if your asynchronous operations return promises, then you'd remove even more boilerplate code from this stuff.
Awesome. Thanks.
Mm-hmm. Mm-hmm. All right, cool. Thank you very much.